So the second talk is being given by Zili Zhang, who's a third-year PhD student at Peking University, advised by Professor Qin Jin. I'm not going to use up more of time. We'll go right over to the talk. So.
Hello everyone, this is Zili from Peking University. Today I'm very glad to share our work, DistTrain, addressing model and data heterogeneity with disaggregated training for multimodal large language models. And this is a joint work from Peking University and Step Fund. Recently, multimodal LLM is becoming an exciting AI paradigm. On the left, we see a unimodal LLM, a chatbot primarily interacting with text. Its capabilities are largely confined to processing natural language and generating code. However, the right side introduces the exciting leap to multimodal LLMs. These models can seamlessly integrate different modalities, not just the natural language and coding, but also from photos, chats, and speech and music. This expansion into multiple senses allows for a much more comprehensive understanding of the world, enabling applications like robotics and even healthcare. And this slide breaks down the typical architecture of multimodal LLM, which can be understood as a three-stage process. First, multimodal input like text, images, and audios are fed into modality encoders. For example, a vision encoder to process images. The crucial output of this stage is a unified interleaved sequence, where all these different modalities are converted into a uniform representations, a sequence of embeddings. This sequence is then passed through an LLM backbone. Here, a powerful model like GPT or Qianwen performs cross-modal reasoning, analyzing the relationships and context between the different types of information. Finally, based on this reasoning, a modality generator such as diffusion model produces the desired modality output, which could be text, a newly generated image, or even audios. However, training such multimodal LLM suffers from two problems models, model and data heterogeneities. First, we will introduce the model heterogeneity and how it affects the training efficiency. Multimodal LLM is a composite of fundamentally different architectures. For example, the modality encoders, often a VIT, is a relatively small transformer with a small hidden dimension. In contrast, the LLM backbone, like GPT, is a heavyweight transformer, often orders of magnitude larger and more complex. And finally, the modality generator is often a completely different architecture, like a convolutional unit. And the key takeaway here is that these components have different designs and computational needs, which leads to different computation time in the pipeline parallelism. To make this problem more concrete, I have plotted the actual forward time of the three modules. As shown in the figure, a 70 billion parameter llama model, a VIT encoder, and a stable diffusion has very vastly different computational cost, but critically, the bottleneck isn't fixed. In the first scenario on the left, when we are processing lower resolution images, the bottleneck is the LLM backbone. However, in the second scenario, if we switch to generating high resolution image, the bottleneck is becoming the encoder and generator, and the LLM backbone has to wait for the encoder and generator to finish. So this model heterogeneity incurs inefficient pipeline bubbles. Now let's turn to the second challenge, data heterogeneity. This slide shows an example of multimodal interaction. The user provides a single prompt that contains multiple tasks. What is the landmark and remove the plants? One task is understanding, the other task is generation. To handle this, the standard training approach is to flatten everything into one non-training sequence. As you can see on the right, in this sequence, the different modality tokens are interleaved. The problem here is that this one-size-fits-all sequence comprises distinct and long-tail multimodal data. Here we conduct a data characterization. This plot shows the distribution of data sizes with the typical multimodal training crops from live dataset. As you can see in the first and second charts, the distribution for text and image subsequences is highly skewed. The vast majority are very short and the minority are very long. The chart on the right shows that a single 8,000 token training sequence may comprise many image subsequences. This distribution is also a long tail. Such a long tail interleaved training sequence leads to training efficiency, since one fixed length sequence with more image tokens may incur more computation in modality generator and encoder. This data heterogeneity leads to distinct types of performance bottlenecks in parallel training. First, on the left, we see the intro-macro batch straggler problem. In an ideal data parallel setup, each DB worker processes a data sample of the same size and finish at the same time. However, if data sample 1 and 2 have more image tokens, DB worker 1 becomes the straggler and blocks the entire training. Second, on the right, this issue extends to pipeline parallelism, creating inter-macro batch stragglers. In an ideal case, each macro batch has the same computation load. However, with data heterogeneity, macro batch A might be image heavy. So such heavy macro batch may become the straggler and prolongs the pipelining warm-up time. So based on the challenge of model and data heterogeneity, which we have just discussed, this slide outlines the co-design of our system DistTrain. To solve the first challenge, model heterogeneity, we introduce disaggregated model orchestration, which means we stop treating the model as an entire unit. Instead, we assign customized independent parallelism strategies to each distinct modulus to best suit their computational need. To solve the second challenge, data heterogeneity, we employ disaggregated data processing. We use intro-macro batch reordering to strategically rearrange the data samples distributed across DP workers. Then we use inter-macro batch reordering to smooth out the flow of the data within the pipeline. Together, these strategies allow DistTrain to adapt to diverse and dynamic nature of multimodal training data. Now let's deep dive into how we solve the first challenge, model heterogeneity. The core issue with the standard approach is that monolithic orchestration, where one single parallelism strategy is applied to the entire model, creates severe performance imbalances. On the left, you can see the typical setup where data, pipeline, and tensor parallelisms are applied uniformly across the entire model. This strategy completely ignores these are architecturally distinct modulars with very different computational needs. So the results are shown clearly in the performance chart on the right. This forces the faster component to sit idle, waiting for the slowest one in the pipeline training. So to address this, our solution is a disaggregated model orchestration, which is designed to dynamically balance its computational loads. As you can see on the slide, we treat each modular as an independent unit and assign a customized parallelism strategy. In the top scenario, where we processing smaller images, we know the number backbone is the bottleneck. Therefore, we allocate more GPU to the LLM. Conversely, in the bottom scenario with high resolution images, the VIT and stable diffusion become the stragglers. So we dynamically reallocate more GPU resources to the encoder and generator. The results are shown in the chat is that the forward passing time for all modulars become nearly equal in both scenarios. And this eliminates the pipeline bubbles and maximize the hardware utilization. This then raises the critical question: how do we automatically and optimally decide the disaggregated pipeline parallelism strategy? To determine the optimal parallelism strategy, we will first need to mathematically model the total execution time. We break down the training process for a batch into two distinct phases. As illustrated in this figure, is the warm-up phase and steady phase. The warm-up phase is the latency for the very first macro batch to complete its journey through all stages of the pipeline. As the first equation shows, this is simply the sum of the computation time for the encoder, the LLM, and the generator. Once the pipeline is full, we enter the steady phase. The performance here, T-steady, is dictated entirely by the slowest stage, the bottleneck, as captured by the max function in the second equation. This slowest stage defines the clock speed for the remainder of the batch. So based on the two equations, we formulate an optimization problem and solve it with the off-the-shelf solvers. Now let's turn to how we solve the data heterogeneity problem, starting with the inter-microbatch straggler. To prevent some data parallel workers from getting unfairly heavy loads, we use a dynamic scheduling technique called inter-microbatch reordering. This process, as shown on the slide, is straightforward but effective. First, before distributing the data for a global batch, we take all the individual data samples and sort them in descending orders based on their computational needs. Then we for each through the sorted list and assign each sample to the data parallel worker that currently has the lowest accumulated workload. So this greedy approach ensures that the total computation loads across all DP instances is almost balanced. This simple reordering minimizes the idle time and effectively eliminates the straggler problem. To solve the inter-microbatch straggler issue within our pipeline, we introduce another scheduling algorithm called inter-microbatch reordering. As the diagram illustrates, a pipeline has a warm-up phase, a steady phase, and cool-down phase. Our reordering algorithm schedules the minimal micro batches, the fastest one to compute at the very beginning and the end of the batch. This allows the pipeline to fill up and drain as quickly as possible. Conversely, the straggler microbatch are deliberately placed within the pipeline intervals in the middle. And this scheduling prevents the stragglers from unnecessarily prolong the warm-up and cool-down period and effectively minimize the pipeline bubbles. So we implement a system prototype with 5,000 of code in Python and C++ on top of Mactron LLM. And we develop a specialized communication library called StepCall. On the left, you can see the key benefit. It's the overlapping the communication and computation by splitting the gem into multiple trunks. The efficient layout in wrapping is to support the trunked computation and communication. This slide shows the workflow of DistTrain. Before we run the system, it will collect the history, execution data to build the profiler. When user gives the numbers of GPUs and the batch of data, DistTrain automatically decides the parallelism strategy according to the profiler results. To evaluate DistTrain, we conducted evaluation using a large-scale setup. Our experiments runs on a substantial hardware cluster consisting of thousands of GPUs. And they are interconnected with a high-performance network utilizing both NVLink and RDMA to ensure efficient communication. And for our training data, we use the production data set from Lime. We combine number 3 with the VIT encoder and the stable diffusion generator as the training model. In the large-scale experiment, we compare DistTrain to Mactron LLM with the monolithic training approach. As the figures show, DistTrain outperforms Mactron LLM by 2.2 times on training throughput and achieves model flops utilization of 54%. For operation study, we use 96 GPUs. To evaluate the effectiveness of the disaggregated model extraction, we choose Mactron LLM as the first baseline. And Mactron LLM represents the standard monolithic orchestration where a single uniform parallelism strategy is applied to the entire model. And our second baseline is DistAM, which employs the more advanced heuristic-based approach. It determines its parallelism strategy from a static matrix like model size and model flops. So as the figures show, DistTrain outperforms all the baseline in all the setup. To evaluate the effectiveness of the disaggregated data processing, which is the down-level reordering, we use Mactron LLM's random order data loader as the baseline. The results show that DistTrain achieves 1.00 to 1.11 times performance gain. So for more evaluation results, please refer to our paper for more details. So finally, I want to conclude the talk. We have demonstrated that large-scale multimodal LM training is fundamentally hindered by the dual challenges of model heterogeneity and data heterogeneity. To solve this, we introduced DistTrain, a novel training system built on 2 core techniques: disaggregated model orchestration and disaggregated data processing. And DistTrain outperforms Mactron LLM by up to 2.2 times on training throughput and achieves model flops utilizations of 54%. By the way, DistTrain already supports large-scale open-source multimodal LLM training. So this is the end of my talk. Thank you very much for listening.
Thank you very much. Really, another good talk. Any questions out there? Oh, right, down here. There's a question. Yes.
Yeah, I want to know, when should we have set up? Yeah, I want to know. Great talk. I'm Mu Yuan from Chinese University of Hong Kong. And I want to know whether, when we just set up the configuration of like the which model we choose, and I want to know whether the optimal pipelining is static or it is dynamic during the training.
In my opinion, this is dynamic, but you can, before training, you can set up a static training parallelism, which is nearly optimal.
Okay, so I think the main contribution of your work is to designing an algorithm to accommodate the pipelining strategy for a different combination of the multimodal training, right?
Sure. I think the main contribution is to disaggregate the different modulars with different architectures. Yeah.
Okay. Cool. Thank you.
Any more questions out there? We have time for one more. I can't see that far, unfortunately. Yes, please. Can somebody get a mic to them?
Oh, thank you. I got a mic. So thank you for your talk. So maybe it's 101 on multimodality training, but I'm still asking. So it seems to me that the very essence of your work builds on the estimation of computational workload for different data chunks within a batch or cross batches. So could you comment on the predictability of the computational workload? Because you've been saying that as you can almost configure a static pipeline that is almost optimal beforehand, right?
As for the predictable, if given a fixed data, a batch of data and a fixed model, in most of the time the computation law is static and which is predictable. But in production level deployment, the data is dynamic. So as in the DistTrain, we have dynamic data reordering online to face the dynamic in online training.
Okay, cool, thank you. But you still have to kind of anticipate, right? You will.
Yeah. The pipeline bubble is inevitable. Yeah.
Okay. Thanks very much. I think we have